Yttrium is a chemical element with symbol Y and atomic number 39. It is a silvery metallic transition metal chemically similar to the lanthanides, and it has often been classified as a rare earth element. Yttrium is almost always found combined with lanthanides in rare earth minerals and is never found in nature as a free element. Its only stable isotope, Yttrium-89, is also its only naturally occurring isotope. In 1787, Carl Axel Arrhenius found a new mineral near Ytterby in Sweden and named it Ytterby, after the village. Johann Gadolin discovered yttrium's oxide in Arrhenius's sample in 1789, and Anders Gustav Eckerberg named the new oxide yttria. Elemental yttrium was first isolated in 1828 by Friedrich Wöhler. The most important use of yttrium is in making phosphors, such as the red ones used in television cathode ray tube displays and in LEDs. Other uses include the production of electrodes, electrolytes, electronic filters, lasers, and superconductors, various medical applications, and as traces in various materials to enhance their properties. Yttrium has no known biological role, and exposure to yttrium compounds can cause lung disease in humans. Section 1. Characteristics. Section 1.1. Properties. Yttrium is a soft, silver metallic, lustrous, and highly crystalline transition metal in group 3. As expected by periodic trends, it is less electronegative than its predecessor in the group, scandium, more electronegative than its successor in the group, lanthanum, and less electronegative than the next member of period 5, zirconium. Yttrium is the first D-block element in the 5th period. The pure element is relatively stable in air in bulk form due to passivation resulting from the formation of a protective oxide, Y2O3, film on its surface. This film can reach a thickness of 10 micrometers when yttrium is heated to 750 degrees Celsius in water vapor. When finely divided, however, yttrium is very unstable in air. Shavings or turnings of the metal can ignite in air at temperatures exceeding 400 degrees Celsius. Yttrium nitride, Yn, is formed when the metal is heated to 1000 degrees Celsius in nitrogen. Section 1.2. Similarity to the lanthanides. The similarities of yttrium to the lanthanides are so strong that the element has historically been grouped with them as a rare earth element, and is always found in nature together with them in the rare earth minerals. Chemically, yttrium resembles these elements more closely than its neighbour in the periodic table, scandium, and if its properties were plotted against atomic number, then it would have an apparent number of 64.5 to 67.5, placing it between the lanthanides gadolinium and erbium. It often also falls in the same range for reaction order, resembling terbium and dysprosium in its chemical reactivity. Yttrium is so close in size to the so-called yttrium group of heavy lanthanide ions that in solution it behaves as if it were one of them. Even though the lanthanides are one row farther down the periodic table than yttrium, the similarity in atomic radius may be attributed to the lanthanide contraction. One of the few notable differences between the chemistry of yttrium and that of the lanthanides is that yttrium is almost exclusively trivalent, whereas about half of the lanthanides can have valences other than 3. Section 1.3. Compounds and reactions. As a trivalent transition metal, yttrium forms various inorganic compounds, generally in the oxidation state of +3, by giving up all of its valence electrons. A good example is yttrium-3 oxide, Y2O3, also known as yttria, a 6-coordinate white solid. Yttrium forms a water-insoluble fluoride, hydroxide, and oxalate, but its bromide, chloride, iodide, nitrate, and sulfate are all soluble in water. The Y3+ ion is colorless in solution because of the absence of electrons in the D and F electron shells. Water readily reacts with yttrium and its compounds to form Y2O3. Concentrated nitric and hydrofluoric acids do not rapidly attack yttrium, but other strong acids do. With halogens, yttrium forms trihalides, such as yttrium-3 fluoride, YF3, yttrium-3 chloride, YCl3, and yttrium-3 bromide, YBr3, at temperatures above roughly 200 degrees Celsius. Similarly, carbon, phosphorus, selenium, silicon, and sulfur all form binary compounds with yttrium at elevated temperatures. Organoyttrium chemistry is the study of compounds containing carbon-yttrium bonds. A few of these are known to have yttrium in the oxidation state 0. The +2 state has been observed in chloride melts and +1 in oxide clusters in the gas phase. Some trimerization reactions were observed by using organoyttrium compounds as catalysts. These compounds use YCl3 as a starting material, which in turn is obtained from Y2O3 and concentrated hydrochloric acid and ammonium chloride. Hapticity is how a group of contiguous atoms of a ligand are coordinated to a central atom. It is indicated by the Greek character eta. Yttrium complexes were the first examples of complexes where carboranyl ligands were bound to a D0 metal center through an eta7 hapticity. Vaporization of the graphite intercalation compounds, graphite Y or graphite Y2O3, leads to the formation of endohedral fluorines such as Y at C82. Electron spin resonance studies indicated the formation of Y3+ and C82 3- ion pairs. The carbides Y3C, Y2C, and YC2 can each hydrolyze to form hydrocarbons. Section 1.4 Nucleosynthesis and Isotopes. Yttrium in the solar system was created through stellar nucleosynthesis, mostly by the S process, approximately 72%, but also by the R process, approximately 28%. The R process consists of rapid neutron capture of lighter elements during supernova explosions. The S process is a slow neutron capture of lighter elements inside pulsating red giant stars. Yttrium isotopes are among the most common products of the nuclear fission of uranium occurring in nuclear explosions and nuclear reactors. In terms of nuclear waste management, the most important isotopes of yttrium are yttrium-91 and yttrium-90, with half-lives of 58.51 days and 64 hours respectively. The first is formed directly from fission, while the latter, despite its short half-life, exists in secular equilibrium with its long-lived parent isotope, strontium-90, with a half-life of 29 years. All group 3 elements have an odd atomic number, and therefore they have few stable isotopes. Scandium has one stable isotope, and yttrium itself has only one stable isotope, yttrium-89, which is also its only naturally occurring one. However, the lanthanide rare earths contain elements of even atomic number and many stable isotopes. Yttrium-89 is thought to be more abundant than it otherwise would be, due in part to the S process, which allows enough time for isotopes created by other processes to decay by electron emission, neutron to proton. Such a slow process tends to favor isotopes with atomic mass number A equals protons plus neutrons around 90, 138, and 208, which have unusually stable atomic nuclei with 50, 82, and 126 neutrons respectively. Yttrium-89 has a mass number close to 90 and has 50 neutrons in its nucleus. At least 32 synthetic isotopes of yttrium have been observed, and these range in atomic mass number from 76 to 108. The least stable of these is Yttrium 106 with a half-life of greater than 150 nanoseconds. Yttrium 76 has a half-life of greater than 200 nanoseconds, and the most stable is Yttrium 88 with a half-life of 106.626 days. Besides the isotopes Yttrium 91, Yttrium 87 and Yttrium 90 with half-lives of 58.51 days, 79.8 hours and 64 hours respectively, all the other isotopes have half-lives of less than a day, and most of those have half-lives of less than an hour. Yttrium isotopes with mass numbers at or below 88 decay primarily by positron emission, proton to neutron, to form strontium, Z equals 38, isotopes. Yttrium isotopes with mass numbers at or above 90 decay primarily by electron emission, neutron to proton, to form zirconium, Z equals 40, isotopes. Isotopes with mass numbers at or above 97 are also known to have minor decay paths of beta- delayed neutron emission. Yttrium has at least 20 metastable or excited isomers, ranging in mass number from 78 to 102. Multiple excitation states have been observed for Yttrium 80 and Yttrium 97, while most of Yttrium's isomers are expected to be less stable than their ground state. Yttrium 78M, Yttrium 84M, Yttrium 85M, Yttrium 96M, Yttrium 98M1, Yttrium 100M, and Yttrium 102M have longer half-lives than their ground states, as these isomers decay by beta decay rather than isomeric transition. Section 2. History. In 1787, Army Lieutenant and part-time chemist Carl Axel Arrhenius found a heavy black rock in an old quarry near the Swedish village of Ytterby, now part of the Stockholm archipelago. Thinking that it was an unknown mineral containing the new element tungsten, he named it Ytterbite and sent samples to various chemists for further analysis. Johann Gadolin at the University of Abo identified a new oxide, or earth, in Arrhenius's sample in 1789 and published his completed analysis in 1794. Anders Gustav Eckerberg confirmed this in 1797 and named the new oxide yttria. In the decades after Antoine Lavoisier discovered the first modern definition of chemical elements, it was believed that earths could be reduced to their elements, meaning that the discovery of a new earth was equivalent to the discovery of the element within, which in this case would have been yttrium. In 1843, Carl Gustav Mosander found that the samples of yttria contained three oxides: white yttrium oxide, yellow terbium oxide, confusingly this was called erbia at the time, and rose-coloured erbium oxide, called terbia at the time. A fourth oxide, ytterbium oxide, was isolated in 1878 by Jean-Charles Galissard du Marignac. New elements would later be isolated from each of these oxides, and each element was named in some fashion after Ytterby, the village near the quarry in which they were found. See ytterbium, terbium, and erbium. In the following decades, 7 other new metals were discovered in Gadolin's yttria. Since yttria was a mineral after all and not an oxide, Martin Heinrich Klaproth renamed it gadolinite in honor of Gadolin. Yttrium metal was first isolated in 1828 when Friedrich Wöhler heated anhydrous yttrium 3 chloride with potassium. YCl3 plus 3K goes to 3KCl plus Y. Until the early 1920s, the chemical symbol YT was used for the element, after which Y came into common use. In 1987, yttrium barium copper oxide was found to achieve high-temperature superconductivity. It was only the second material known to exhibit this property, and it was the first known material to achieve superconductivity above the economically important boiling point of nitrogen. Section 3. Occurrence. Section 3.1. Abundance. Yttrium is found in most rare earth minerals, as well as some uranium ores, but is never found in nature as a free element. About 31 parts per million of the Earth's crust is yttrium, making it the 28th most abundant element there, and 400 times more common than silver. Yttrium is found in soil in concentrations between 10 and 150 parts per million, dry weight average of 23 parts per million, and in seawater at 9 parts per trillion. Lunar rock samples collected during the American Apollo project have a relatively high content of yttrium. Yttrium has no known biological role, though it is found in most, if not all, organisms, and tends to concentrate in the liver, kidney, spleen, lungs, and bones of humans. There is normally as little as 0.5 milligrams found within the entire human body. Human breast milk contains 4 parts per million. Yttrium can be found in edible plants in concentrations between 20 parts per million and 100 parts per million fresh weight, with cabbage having the largest amount. With up to 700 parts per million, the seeds of woody plants have the highest known concentrations. Section 3.2 Production. The chemical similarity of yttrium with the lanthanides leads it to being enriched by the same processes and ends up in ores containing lanthanides, forming rare earth minerals. A slight separation is recognized between the light LREE and the heavy rare earth elements HREE, but this separation is never complete. Yttrium is concentrated in the HREE group, even though it has a lower atomic mass. There are 4 main sources for REEs. 1. Carbonate and fluoride containing ores such as the LREE, bastnasite, Ce, La, etc., CO3F, contain an average of 0.1% of yttrium compared to the 99.9% for the 16 other REEs. The main source for bastnasite from the 1960s to the 1990s was the Mountain Pass rare earth mine in California, making the United States the largest producer of REEs during that period. 2. Monazite, Ce, La, etc., PO4, which is mostly phosphate, is a placer deposit of sand that is created by the transportation and gravitational separation of eroded granite. Monazite as an LREE ore contains 2% or 3% of yttrium. The largest deposits were found in India and Brazil in the early 19th century, making these 2 countries the largest producers of yttrium in the first half of that century. 3. Xenotime, a REE phosphate, is the main HREE ore containing up to 60% of yttrium as yttrium phosphate. The largest mine for this mineral is the Bayan Obo deposit in China, making China the largest exporter for HREE since the closure of the Mountain Pass mine in the 1990s. 4. Ion absorption clays or Lognan clays are the weathering products of granite and contain only 1% of REEs. The final ore concentrate can contain up to 8% of yttrium. Ion absorption clays are mostly mined in southern China. Yttrium is also found in samarskite and fergusonite. It is difficult to separate yttrium from other rare earths. One method to obtain pure yttrium from the mixed oxide ores is to dissolve the oxide in sulfuric acid and fractionate it by ion exchange chromatography. With the addition of oxalic acid, the yttrium oxalate precipitates. The oxalate is converted into the oxide by heating under oxygen. By reacting the resulting yttrium oxide with hydrogen fluoride, yttrium fluoride is obtained. Annual world production of yttrium oxide had reached 600 tons by 2001, with reserves estimated at 9 million tons. Only a few tons of yttrium metal are produced each year by reducing yttrium fluoride to a metal sponge with calcium-magnesium alloy. The temperature of an arc furnace of above 1,600 degrees Celsius is sufficient to melt the yttrium. Section 4. Applications. Section 4.1 Consumer. Yttria Y2O3 can serve as a host lattice for doping with Eu3+ cations, as well as reactant to gain doped yttrium orthovanadate YVO4 with Eu3+, or yttrium oxide sulfide Y2O2S with Eu3+, phosphors that give the red color in color television picture tubes, though the red color itself is actually emitted from the europium while the yttrium collects energy from the electron gun and passes it to the phosphor. Yttrium compounds can serve as host lattices for doping with different lanthanide cations. Besides Eu3+, also Tb3+ can be used as a doping agent, leading to green luminescence. Yttria is also used as a sintering additive in the production of porous silicon nitride, and as a common starting material for both material science and for producing other compounds of yttrium. Yttrium compounds are used as a catalyst for ethylene polymerization. As a metal, it is used on the electrodes of some high-performance spark plugs. Yttrium is also used in the manufacturing of gas mantles for propane lanterns, as a replacement for thorium, which is radioactive. Developing uses include yttrium-stabilized zirconia, in particular as a solid electrolyte, and as an oxygen sensor in automobile exhaust systems. Section 4.2 Garnets. Yttrium is used in the production of a large variety of synthetic garnets, and yttria is used to make yttrium iron garnets, Y3Fe5O12 or YIG, which are very effective microwave filters. Yttrium, iron, aluminium and gadolinium garnets, for example Y3Fe or Al5O12 and Y3Fe or Ga5O12, have important magnetic properties. YIG is also very efficient as an acoustic energy transmitter and transducer. Yttrium aluminium garnet, Y3Al5O12 or YAG, has a hardness of 8.5 and is also used as a gemstone in jewelry, simulated diamond. Cerium-doped yttrium aluminium garnet, YAG-Ce, crystals are used as phosphors to make white LEDs. YAG, yttria, yttrium lithium fluoride, LiYF4, and yttrium orthovanadate, YVO4, are used in combination with dopants such as neodymium, erbium, ytterbium in near-infrared lasers. YAG lasers have the ability to operate at high power and are used for drilling into and cutting metal. The single crystals of doped YAG are normally produced by the Czochralski process. Section 4.3 Material Enhancer. Small amounts of yttrium, 0.1 to 0.2%, have been used to reduce the grain sizes of chromium, molybdenum, titanium, and zirconium. It is also used to increase the strength of aluminium and magnesium alloys. The addition of yttrium to alloys generally improves workability, adds resistance to high-temperature recrystallization, and significantly enhances resistance to high-temperature oxidation. See graphite nodule discussion below. Yttrium can be used to deoxidize vanadium and other non-ferrous metals. Yttria is used to stabilize the cubic form of zirconia for use in jewelry. Yttrium has been studied for possible use as a nodulizer in the making of nodular cast iron, which has increased ductility. The graphite forms compact nodules instead of flakes to form nodular cast iron. Yttrium oxide can also be used in ceramic and glass formulas since it has a high melting point and imparts shock resistance and low thermal expansion characteristics. It is therefore used in camera lenses. Section 4.4 Medical. The radioactive isotope Yttrium-90 is used in drugs such as yttrium Y90 DOTA Tier 3 octreotide and yttrium Y90 ibritumomab tiaxetan for the treatment of various cancers including lymphoma, leukemia, ovarian, colorectal, pancreatic and bone cancers. It works by adhering to monoclonal antibodies, which in turn bind to cancer cells and kill them via intense beta radiation from the Yttrium-90. See monoclonal antibody therapy. Needles made of Yttrium-90, which can cut more precisely than scalpels, have been used to sever pain-transmitting nerves in the spinal cord. And Yttrium-90 is also used to carry out radionuclide synovectomy in the treatment of inflamed joints, especially knees, in sufferers of conditions such as rheumatoid arthritis. A neodymium-doped yttrium aluminium garnet laser has been used in an experimental robot-assisted radical prostatectomy in canines in an attempt to reduce collateral nerve and tissue damage, whilst the erbium-doped ones are starting to be used in cosmetic skin resurfacing. Section 4.5 Superconductors. Yttrium was used in the yttrium-barium copper oxide YBa2Cu3O7, also known as YBCO or 123 superconductor, developed at the University of Alabama and the University of Houston in 1987. This superconductor operated at 93 Kelvin, notable because this is above liquid nitrogen's boiling point, 77.1 Kelvin. As the price of liquid nitrogen is lower than that of liquid helium, which has to be used for the metallic superconductors, the operating costs would decrease. The actual superconducting material is often written as YBa2Cu3O7-D, where D must be less than 0.7 if the material is to be superconducting. The reason for this is still not clear, but it is known that the vacancies occur only in certain places in the crystal, the copper oxide planes and chains, giving rise to a peculiar oxidation state of the copper atoms, which somehow leads to the superconducting behavior. The theory of low-temperature superconductivity has been well understood since the so-called BCS theory was put forward in 1957. It is based on a peculiarity of the interaction between two electrons in a crystal lattice. However, BCS theory does not explain high-temperature superconductivity, and its precise mechanism is still a mystery. What is known is that the composition of the copper oxide materials has to be precisely controlled if superconductivity is to occur. The created material was black and green, multi-crystal, multi-phase mineral. Researchers are studying a class of materials known as perovskites that are alternative mixtures of these elements, hoping to eventually develop a practical high-temperature superconductor. Section 5 Precautions. Water-soluble compounds of yttrium are considered mildly toxic, while its insoluble compounds are non-toxic. In experiments on animals, yttrium and its compounds cause lung and liver damage, though toxicity varies with different yttrium compounds. In rats, inhalation of yttrium citrate caused pulmonary edema and dyspnea, while inhalation of yttrium chloride caused liver edema, pleural effusions, and pulmonary hyperemia. Exposure to yttrium compounds in humans may cause lung disease. Workers exposed to airborne yttrium europium vanadate dust experienced mild eye, skin, and upper respiratory tract irritation, though this may have been caused by the vanadium content rather than the yttrium. Acute exposure to yttrium compounds can cause shortness of breath, coughing, chest pain, and cyanosis. NIOSH recommends a time-weighted average limit of 1 mg per meter cubed and an IDLH of 500 mg per meter cubed. Yttrium dust is flammable.